Okay, so good morning, everyone. Welcome to our second keynote speech in this conference. So let me begin with one question. How many of you don't have mobile phone? So I guess nobody can say yes. So almost everyone nowadays has a mobile phone. Some has multiple ones. So cellular security is therefore very, very critical to everyone. However, as a researcher, if you feel that cellular security is no more than secure communications between mobile devices and the base stations, then I think today's talk probably will change your opinion towards this topic. It is much deeper than you have thought before. It is my great pleasure and honor to introduce you our keynote speaker, Professor Yongdae Kim. He's currently a professor at the Department of Electrical Engineering and the Graduate School of Information Systems at KAIST. He served as a KAIST chair professor between 2013 and 2016, and is a director of the CyberSec Research Center between 2018 and 2020. Before joining KAIST, he was a professor at the University of Minnesota, Twin Cities for 10 years. Yongdae has served on many conferences. He's currently the program chair for YSEC and was also the general chair for last year's CCS. He served as an associate editor for ACM Transactions on Privacy and Security and sits on the steering committee of NDSS. And last but not least, Yongdae was my academic brother, 1 year senior than me. So I still remember when I was a PhD student, Yongdae was the role model to me and to other junior students. So I learned, I should say this, I learned a lot of things from Yongdae, including how to do research, how to work, how to deal with people. So please allow me to abuse this opportunity to say thank you to Yongdae for those memorable 4 years in USC and in Irvine. Okay, now without further ado, let's welcome Professor Yongdae Kim to talk about cellular security.
All right, thank you, Shua and Katsuya. And this is my great pleasure to give a keynote in ASIACCS. You know, I'm rooted at the ASIACCS, and I'm also rooted at the Asia, and also I have many friends. I had many friends in Japan, even though when I was working on crypto, but I don't work on crypto anymore. But anyway, so yeah, this is my great pleasure to talk about cellular security and why it's difficult. And I gave a version of this presentation in 2019 in Qualcomm Product Summit, Security Summit as a keynote. So I was invited to Qualcomm to talk about cellular security, overall view about cellular security. And since then, already 3 years have passed, and quite a bit of changes already have made. But I still think there are many, many, many problems, and I want to talk about those problems. So let's start. So let me introduce myself a little bit more. So yeah, so these I talked about. I mean, Shua already introduced, and I usually work on emerging technologies such as drone, blockchain, medical devices, self-driving cars, and cellular. And about half of my students are working on cellular security. And our lab usually find vulnerabilities and report to vendors such as Qualcomm, Samsung, Apple, Huawei, and cellular carriers. And so in that sense, we find a lot of vulnerabilities, yeah. And in the last 10 years, so I first published a cellular security paper in 2012, and this year is 2022. Yeah, I published several papers. And most of these papers are actually finding vulnerabilities and bugs. And because I found those vulnerabilities, we had to do like a responsible disclosure. And during the responsible disclosure, we had to talk with actually many of the industry as well as the cellular standard bodies, as well as the governments. And while communicating with them, I learned a lot about the industry and also the nature of the cellular industry. And those the communication with them actually helped me to understand the cellular security much better. So yeah, so this is kind of summary of my, how many papers? It's like 12 to 13 papers, and what was my experience and what I learned by writing these papers and communicating with the industry, government, and standard bodies. So are we done with these papers? No, actually, I have several more papers on pipe, and some papers got rejected, right? So the question I'd like to discuss today is why cellular networks, devices, and protocols have so many security problems. If you know, the cellular security started from 2G, right? I mean, people started using 2G, 3G, 4G, 5G, and some people are talking about 6G, right? Over 40 years, we've been developing cellular, and over 40 years, we've been working on security. Why cellular networks, devices, protocols have so many security problems? This is what we want to answer. So before getting into the details, let me talk about a brief introduction to cellular system. So cellular system is actually a very, very complicated system. And here's your phone, right? Your phone has a hardware chip called modem. And in addition to the modem that speaks the cellular protocol on your user equipment side, we call UE as a phone, right? With the modem, you also need a SIM card called USIM. And USIM is actually a very small hardware chip. And your phone first communicate with a cell tower. And then your communication is split into two different ways. The solid line is a data plane communication. So S gateway, P gateway. Oh, so I'll be talking about LTE because 5G is not that different and LTE is easier to explain. So there are two gateways. One is called S gateway and the other is P gateway. P gateway is looking for the internet and S gateway is looking to the cellular networks. And you may have like a billing functions implemented in P gateway. So this means that actually the packets not arriving in your phone may be accounted. Yeah. And instead of this infrastructure base stations, you may have a home node B, which is the cellular, the cell tower in your home. And this looks like a Wi-Fi AP. So this is actually your data flows, but also there are multiple control plane operations. For example, routing, authentication, and mobility management, those are all provided through the control plane operation. And so to have a ring and all those operations are going through the this control plane. And there are two major entities. MME is a mobility management entity. Hold on. Yeah. And HSS is in charge of the authentication. And sometimes you may have actually firewall and net boxes for preventing some kind of DDoS attacks. So these are, very, very out. And there are some more components, and your network can be connected to another network through roaming. And so this is a global cellular network. And also your network is also connected to 2G and 3G. So 4G to 2G to 3G connection also survives. So yeah, so it's a very, very complicated system. And let me talk about briefly where those vulnerabilities exist, and we will revisit those vulnerabilities. And in the access network, we call this user equipment and cell tower and home inode B as access network. And even in this access network, you may have actually various cellular problems. And especially, you may think the SIM card has no problem, but these days, as you have seen with the lapses, the SIM cloning and SIM spoofing, it's getting really, really, really popular. And your modem baseband has also cellular problems, and you may use fake base station. And also when you use femtocell or home inode B, so this is like a typical embedded device, so you may have other vulnerabilities as well. So all the edge node have actually quite a bit of vulnerabilities previously and still have those vulnerabilities. And in the core network, there are more and more problems, and there are like a temporary ID issues for privacy preservation, and accounting had a lot of problems as well. And when you use netbox and firewalls, and their rules have vulnerabilities as well. And then in the service layer, you may have actually also a lot of problems. And voice over LTE, or we call it VO 5G in case of 5G network. So your voice communication is now implemented using data, and they have a lot of security problems. And roaming service has been known to have many, many, many vulnerabilities. And now they are developing some enhanced cellular services, or cellular services with the special purpose cellular services, such as controlling railroad communication and public safety LTE used by police and military service as well. So yeah, so I mean, when there was no component which does not have any security problems, right? And let me talk about why we have cellular security problems. And actually, this is the most important part. If you understand this part, then you may be able to start doing the research. So there are some meta issues. What I mean is that this is not really a technical issue, but this is more like a political or business aspect of the cellular industry, which you cannot avoid having security problems. First, cellular technology. In case of cellular, they have new generation every 10 years. So 2G, 3G, 4G, 5G, and we are preparing 6G. So in every generation, it took about 10 years to go to the next generation. And each generation, when you talk to 3GPP folks, they say, oh, we are developing clean slate, right? Clean slate means you have new standards, completely new standards written from scratch, and new implementation, completely new implementation, and completely new deployment. And as we know, when you do new implementation, we have new vulnerabilities in software. And I mean, so this is worse because you have a new design, meaning that you have new design vulnerabilities, and you have a new implementation vulnerabilities, and you have a new deployment vulnerabilities, right? And that's like a new software has always new vulnerabilities. So, and this is like a worse because you have everything from scratch, right? And another interesting problem with the cellular is that there is a generation overlap period. So in case of cellular, so between 3G and LTE, there was a time called CS fallback. CS fallback means it's a socket switching fallback. So when people started LTE, the voice, so LTE is a or IP technology. So LTE will use everything in IP communication, but the voice was not ready. So when the voice was not ready, they were using 3G voice. I mean, some of the old folks here probably remember it. So we were using 3G voice and LTE data, okay? So at that time, the problem was there was a vulnerability in 3G, there was a vulnerability in LTE, and the combining technology had also vulnerabilities. And when you talk to 3GPP, they say, oh, the CSFP will be destroyed pretty soon, so we are not going to patch it. So they think these are kind of temporary technologies, but these technologies have been used for like 5 years. And for 5 years, those temporary technology has never been fixed. And another problem with the cellular security is backward compatibility. So whenever you, so I think even in Korea and Japan and China, there are still many 2G users. And people say, and because the users have 2G phones, people say, oh, you have to support 2G cellular. But 2G is completely vulnerable, and you can eavesdrop on 2G network. And because it is backward compatible, that means an attacker can do the, downgrading attack to 2G. So even if you are a 5G user, they can downgrade you to 2G and eavesdrop on you. So that's another problem. And there is a clear ordering between the participating entity in the cellular networks: government, carrier, device vendors, and customer. So government, I think, is the most important party who decides cellular policy. And they are not, I mean, actively participating in the standard writing, but it seems that they are deciding on many of the policies, okay? And between the carrier and device vendors, because the carrier buys device vendors' product, device vendors have to follow carrier's order. So even if the carrier is asking insecure option, device vendors have to follow. And it seems that customers are not that important because these three entities will decide their policy, and the customer is thought as the last people, and they try to hide as much as possible from the customers. And the another problem, it's a bad problem existing in cellular, is that it's a walled garden, meaning that basically those carrier and device vendors have actually big, thick, very thick wall between them and against the customers. And carriers and vendors don't talk to each other about their technical problems. And because they don't talk about their technical problems, they experienced the vulnerabilities have not been exposed to others. And when, according to our experience, most of the carriers, they do not respond to responsible disclosure. Even though we respond, we disclose our vulnerabilities, they say nothing. Right? And the last is actually, this is not really a technical problem, but because you have like a new technology like every 10 years, that means you need new open source development softwares and you need new hardware for communication. But because this open source development is slower than commercial development, you don't have actually any tool to do real research. Like for example, for 5G SA standalone, we don't have actually radio to do software radio communication, and or it's too expensive to use, right? So this is not really technical problem, but makes the whole cellular industry pretty bad for security. And let me talk about some standard issues, and these are standard and specification issues. So cellular standard is actually very, very complicated, and it's a huge. And because it's a huge, it's very thick. For example, the RRC, which is the standard between your phone and your cell tower, for LTE was like 1,000 pages. Okay, of course there's a separate security document, but that's like a huge. And MME was like 600 pages. Already, I don't know how much detail my students understand, but as I told you, I have like 11 students working on cellular security. Okay, unless those 11 students read those standards, probably we will not be able to catch up with all the standard changes, right? So huge standard is a problem. And the second problem is there are quite a few unpatched design vulnerabilities, and I'll be talking a lot more about these details, but some of the vulnerabilities have been pointed out from the 2G or 3G. They have not been fixing it, maybe because it's too costly for carriers, right? Carrier try to save their money. And this is always the case for network security, that network security cannot survive without standards, right? And standard is usually written with natural languages. Because it's written in natural languages, people misunderstand the standard. By vendors and carriers, they misunderstand the standard and misimplement, or misdeployment happens because it's difficult to understand the exact meaning. And if you want to do formal analysis, probably you need to convert your specification to state machine. But converting the specification to state machine is actually a very difficult problem, because you need many domain knowledge is required to understand the actual specification. To make it worse, 3GPP standard leave many implementation details for vendors. One of the famous of this case was, they say, the standards say you have to prevent replay attack. Nothing, but you have to prevent replay attack. then the standard has to check whether the replay attack prevention is implemented correctly, but no one checks if the replay attack prevention is doing correctly, right? That means you may have replay attack. And cellular networks devices could be actually different from each carrier and vendors, meaning that because of the misunderstanding on the standard, they may have a misimplementation and misdeployment that actually prevents and that result in diversification as well. That means the vulnerabilities could be different. So even though there is one standard, because there are so many options and there are so many possibilities and so many misunderstandings, you may have actually completely different vulnerabilities, unexpected vulnerabilities. despite this, why the cellular network works? Because they have something called conformance testing standard. Conformance testing standard checks if good messages, meaning that no error message. So other than the error messages, if those good messages are working fine. So they check good messages are working fine. However, there is no security, almost no security testing standard, meaning that they don't check if invalid or prohibited messages are handled correctly in standard. So there is no such standard, meaning that there is no security testing, meaning that you may have actually a lot of vulnerabilities. So these are already a list of like 12, 13, 14 problems, which will be very hard for cellular industry to make it secure. And I think this is major problem, because from the government point of view, I'm not sure whether they are interested in securing their infrastructure. And from Korea's perspective, because when there is a vulnerability, who's losing data? It's customers, right? But the government and carriers decide their policy. So from their perspective, from carriers' perspective, even testing for security is a cost. And I don't know whether they are incentivized to do the security testing, right? So let's get into the details, technical aspect, and I'll give you some of the examples supporting my argument previously. So let's start with I cannot do whole comprehensive study because this is a limited time, and I'll give you a few examples first. So CMAS is an emergency SMS protocol. So it's an emergency SMS messages. Hold on. So the cell tower was actually communicating with the UE normally, but when emergency happens, like an earthquake happens, then cell tower broadcast some messages. So the first message is, it is a broadcast message to all the cell phones. Hey, I'm going to send the emergency SMS message. Okay. Then existing connections are all teared down, and so your phone will get ready. And SIB1 and SIB2. So SIB is like a signal system information block, and this is like a broadcast message from your cell tower. So emergency SMS is different from the SMS because it's not pairwise communication. So cell tower decide to broadcast, and cell tower just broadcast the emergency SMS messages. Okay, because this is a completely broadcast message, to know whether this is authenticated, you need to have digital signature, right? It's a broadcast message, and to know whether this is actually from the legitimate cell tower, or is it from maybe fake broadcasting station, you need digital signature, right? But there is no digital signature in the standard. That means you can actually implement fake base station like this, and then you can actually spoof cell towers communication. And let me give you a brief demo. So this is very easy as long as this phone is subscribed to this fake base station, and you just need a strong antenna and strong power. Then your phone will be subscribing to this fake base station instead of the commercial cell tower. As I told you, the broadcast message from the cell tower to your phone is not authenticated. And also, because of the nature of wireless communication, before you are on the, so when you think about the wireless communication, or even in case of Wi-Fi, your device is first connected wirelessly, and then authentication happens, right? So that means pre-authenticated messages cannot be authenticated. If the pre-authenticated messages are not authenticated, because you are pre-authentication state, that means your device may be connected to fake base station, like the previous example. Once you are connected to fake base station, then the fake base station may control your device by sending fake emergency SMS message, as I told you. And some of the messages, cellular messages, are not even authenticated. So in cellular security, people are using message authentication code in the standard, following the standard, but some of those, like attach reject messages, detach messages, or service reject messages, these messages are not even authenticated. So that means fake base station may actually send those reject messages to actually denial of service attack on you. So once the phone is connected to fake base station, these attacks are possible. And there is another variation of this attack. In case of fake base station, the phone has to actually subscribe to fake base station. But I think the more important problem is that cell tower to UE, the broadcast message is not even authenticated. Then you may think about this kind of clever attack. So while the cell tower is broadcasting messages to UE, right? Maybe the attacker can modify one of the subframe, which is just maybe 0.1 millisecond short. Okay, so because there is no message authentication in the broadcast messages, that means attacker may inject in the physical layer this kind of attacker's frame that can be arrived on the UE. Of course, to implement this, it requires quite a bit of hardware engineering and physical layer attacks. But after, one of my students spent full 2 years. So from his perspective, he spent like a full 2 years to implement this. But after 2 years, the attack works really well. Now the SIGOver attack is open sourced, and you can do the experiment if you have radios. And I'll give you a demo of signal overshadowing attack. And let me skip early part. Yeah. So it shows that the attack. So your phone is working normally, right? And the phone call works, and then let me skip. Right. Yeah. And then we will do signal injection on the wire. So the phone is still connected to commercial network, but we are injecting the particular subframe. We are replacing the particular subframe. And this is from the Wireshark, and it will show that these messages are injected on the commercial messages. And so the message contains, the cell tower to the UE, the phone say that, I'm too busy, so please do not connect me. So cell tower tells the UE that I'm busy, then the UE is actually disconnected. And none of the data communication works. And even phone does not work either. Yeah, nothing works, right? So even after attack stops, the cell tower tell the UE be quiet for a while, then your phone becomes quiet, right? So this is basically, yeah. So these were a series of insecure design. So there are many insecurity in standard. Broadcast messages are not authenticated at all. And roaming networks such as SS7 and Diameter assumes that the carriers trust other carriers, meaning that your SMS messages will not be encrypted and routed to another carrier, meaning that when you are roaming to another country, then another country's government may be able to look at your SMS messages. Maybe because of the standard called Lawful Interception, the cellular communication allows or has to support decryption by the standard, which allows the government can take a look at your messages all the time. And before authentication, before pre-authentication stage, their initial messages should be unauthenticated. And voice encryption is only, so the encryption happens between your device to cellular tower. So after passing the cellular tower, your data and voice is not really encrypted. And for basic authentication, it still uses symmetric key-based authentication and key management. I've heard from Andrew Odlytsko, the great cryptographer, that when people were designing 3G, people told them, the researchers told them, let's use public key cryptography for authentication. So there was like 30 years ago, people asked them to use public key cryptography for authentication, but they are still not using public key cryptography. Maybe 30 years ago, the performance was the issue, but not anymore. And we don't know, I mean, we have to know in detail why they are not implementing. The question is, suppose you implement a cellular network such as 6G from scratch. Will you design with these insecurities, or you want to design cellular security clean slate? Right? So I just talked about design issues, and I don't have many time. So I still have plenty of slides. So as I told you, new systems have a new vulnerability. And I'll give you just one quick example. Was our CCS 15 paper. So at that time, we wanted to check whether VoLTE, so as I told you, 3G was using socket switching, and LTE is using packet switching, VoLTE is using packet switching, and a lot of parts were changed. So what we tried to see is, okay, the 3GPP standard has to change. Mobile operating system should change a little bit because of the socket switching to packet switching. Device hardware interface should change. Accounting should change. Implementation of the LTE core because the new IMS server should appear. So these had to be changed. And we made about like 80 test cases to see if those changes are implemented correctly, right? And what we found, every part have a problem. So this is the nature of the argument, I say. When you have new design, new implementation, and new deployment, then you will have these kind of vulnerabilities. And the vulnerabilities are critical: message manipulation, wiretapping, caller spoofing, denial of service attack, caller spoofing. And there are many free unaccounted channels as well, right? And in one of the Korean telcos have every bypassing of account as well as the vulnerability was possible. But even in the US major telcos, they have quite a bit of vulnerabilities, right? So do you believe me? When you design new system and newly implement and newly, we always tell the people that for cryptographic mechanisms or for security mechanisms, you need the scrutiny. But there is no such scrutiny in cellular security. Therefore, I think we need to develop more technology for cellular security testing. So we've been doing a lot of cellular security testing on cellular modems, cellular network devices, and cellular carrier networks and standards. And these are the summary of why the testing is necessary, because new generation every 10 years, complicated and huge standard, ambiguous standard, leave many implementation details for vendors, and they could be different. Conformance testing suite exists, but no security testing standard makes security testing a necessary component of the cellular security. And many combinations are possible. And so there is a static analysis, dynamic analysis, comparative analysis, negative testing. Negative testing means you intentionally generate violating messages and see those violating messages or exceptional messages could be handled correctly. And formal analysis, state machine, specification, traffic, binary analysis, when you have source code, modem, devices, specification. So these are the keywords, right? And the 5 papers we covered were target on, so mostly other than CCS 15 paper, every paper was targeting the most important two protocols. NAS is communication between your phone and the core network, including the authentication. And RRC is the communication between your phone and the cell tower. And when you look at it, so in case of Volte, it was a static and dynamic analysis, and we had to do reverse engineering on the modem, and we tested on the carrier networks as well. And we found vulnerabilities in the device as well. And we also generate some violating messages to see if it is properly handled. So since then, our kind of testing has been more focused. And TMC 18 paper was more about finding design errors, or we want to understand comparative analysis, because not every network made mistakes. So we were trying to check whether we may be able to learn from others. And SMP 19 was actually, we tried to find, through dynamic testing and negative testing, we tried to find vulnerabilities on the carrier networks. And NDSS 21 was actually the first static approach, finding vulnerabilities in the modem binaries, right? So let's talk about these 5 papers briefly and see why, to support our claims and to talk about the future directions. And to show that the vulnerabilities is worldwide problems, actually, when my students traveled to conferences, they were collecting traffic. They intentionally made calls. And so in 11 countries, over 28 operators, we collected 95 USIM cards and made 52,000 robot calls. Okay. Through 52,000 robot calls, we generate about 6.4 million signaling messages, and we try to find anomalies. We try to find anomalies instead in the timing threshold and control flow the ordering of the control flow messages and some failure messages, and we try to see if there are any errors. If we see very, very strange events. And we found very, very strange bugs. And so like these are the bugs: out of service for 11 seconds, 3D detach is delayed, and out of service for 30 seconds, and stuck in 3G for 100 seconds, blah, blah, blah. And so these are strange bugs. But this particular bug was happening only in US too. And this particular bug out of 28 telcos, but this bug was happening only in 5 telcos. And this was only one Deutsche Telekom, I mean German Telecom. And this was Spain and US too. So what do you see here? They're all different. And we don't know who is implementing better. But one of the interesting things is that there is no Korean telco. Meaning the Korean telcos are actually doing pretty well. And there is no Japanese telco, maybe because we couldn't collect traffic from Japan. And we couldn't collect traffic from Singapore either, right? But what I want to say is that there are very few actually network vendors. Probably Samsung, Nokia, Huawei, Ericsson, those are 4 main vendors, and probably Cisco. There are 5 device vendors, and we have gazillion of carriers. And we just checked 28 carriers, and we have this kind of localized vulnerabilities. And to check if this is correct, we also wanted to check whether the state machine we collected from the network was stable or not. And this is kind of animation of the state machine of different networks. Do you see the state machine changes? And some main state stays the same, but actually they have different implementations. So this is actually very strange because there are only 5 network device vendors. It's very, very weird. So we decide to work on, okay, so you may have actually complete research plan about what we can do is, so because when you see these kind of differences, then probably comparative analysis is the best way to go. The first one is you can actually collect control plane messages by injecting events. You may be able to collect control plane messages from different carriers, right? And then you can actually build a state machine using the control plane messages, and you may be able to compare them. And also from the 3GPP specification, maybe NLP, maybe using NLP or maybe using human help, you may be able to build your state machine. Then you may be able to compare between or compare among those carrier networks as well, right? And once you have actually protocol modeling formally, then you may be able to do formal analysis. I mean, it's a lot more, I mean, much harder scale than, you know, ProVerif or Spin or Tamarin or those formal analysis is actually too, I mean, it's not scalable. But if you can do a little more scalable approach, then you may be able to do formal analysis, right? And you may be able to, once you fix the vulnerability, then you may be able to compare the specification, the fixed specification against the, you know, state machine in the network as well, right? I'm like 10 minutes left. And then you may be thinking about how to improve the security. But I mean, as you see, the comparative analysis worked pretty well, right? So the comparative analysis pretty well in NDSS 21, we actually compare baseband software and cellular specification because humans are involved in multiple places that may have different understanding or different implementations. So what we did in BaseSpec was actually we download the specification and we parse the table contains in the specification, and we cut out the message structure from the specification, and through formal binary analysis, and we found the message structure. And by comparing message structures, we can do synthetic comparison between the standard and the binary. And also, we may be able to do comparison between message structure and L3 decoder to find semantic comparisons. And these comparisons will show the difference between the specification and binary. And this allows us to find other vulnerabilities or errors as well. Right. And there were, from one of the vendors, there were many error cases, and we were able to find memory errors, including remote code execution as well. And let's move to the negative testing because I need more time. Yeah. So the first approach we think was, so can we test network and can we test devices for handling bad cases? So in the first paper, the touching the untouchable paper, we just picked 3 major properties. For example, the plain messages will cause problems, and the MAC should be handled correctly, and replay attack should be handled correctly, and authentication mechanism should be implemented correctly. And in those 3 cases, we try to generate traffic that violate each of these security properties. And those violating security properties, so we inject those messages to the cellular network and UE side. And of course, when we inject the traffic to this cellular network, we had access to the core network's testbed. So Telco gave us testbed to test our test cases. And because in most countries, this is illegal. So we were able to inject those test cases to find vulnerabilities by injecting violating messages. And these were the surprising result. And that's why this paper got a lot of attention. And NASA and RC implementation, we found actually many errors. The B is fine, but all the other characters, B and hyphen is fine, but the rest of the stuff is all attacks possible. So these were the vulnerabilities we found in the network. So the core network side and baseband side, and we generate very few messages for core network and core networks, but still we found actually many vulnerabilities. So just simply injecting violating messages. And this is the slide I want to show that actually they have different implementation. And this MME1, so these are 2 carriers in Korea. Okay, carrier 1 has MME1 and MME2, carrier 2 and MME3, and MME1 and MME3 are from the same vendor. But if you see them, actually they have different vulnerabilities. You see what I'm saying? That they even inside Korea, the carriers set their system differently, and they have different vulnerabilities. So after writing this paper, we were actually talking to 3GPP. You should do security testing as a standard. And they say no, because, and I said the negative testing is necessary. And they say, oh, you cannot list them. How do you list negative test cases? Yeah, that is difficult question. So we decide to look at the standard carefully and check, generate test cases. So we have generated about 2,800 test cases to test your user equipment. And by looking at the response messages, we were able to, so this is actually like a fuzzing, but we try to find semantic bugs through fuzzing, right? And this allows, because we are sending out illegal messages, we need to get some kind of error messages or ignorance on the messages, or we can do actually comparative testing to find bugs as well. Okay, so, and we tested against 43 phones, and these are the types of bugs we found, and different phones, and even from the same vendor, different phones, and different phones has different kinds of vulnerability. All right, so I'm like very much over. So let me conclude my talk. So in cellular security, there are many design vulnerabilities. And some of those design vulnerabilities are not patched because of technical problems, as well as political problems. And maybe the clean slate design it is not clear state. As clean slate design may be necessary for 6G for handling this cellular privacy problems. And I think specification could be written better. If I think they have to be formally verifiable. And also, I think they need to provide sample implementation to avoid implementation errors. And I think the negative testing still should be standardized. And some people try use of NLP to understand the 3GPP specification or other network standard specification. But it seems that it's impossible because there are so many inconsistencies in the specification because it worked by humans. And there are a lot of ambiguities, and domain knowledge is required as well. And I still hope for binary versus source code versus specification comparison. But we did some initial work, but it seems that because of the difficulty in each field, still a long way to go for a comparative study. Thank you very much.